So this is my second video recording the Workthrough to 2021 Specialist Maths Exam 2. The first question is on rational functions and graphs and a bit calculus. So first part, we would like to express this f of x in the form a plus b x plus c divided by x minus 1 times x plus 2. So this is a proper fraction form instead of a partial fraction form. Using the CAS calculator, we can define f of x first and then use the command propfrac, and this is the required answer. So we can just write f of x as 2 plus 5x minus 11 divided by x minus 1 times x plus 2. And if I further expand the function into partial fraction form, we can see there is a 7 over x plus 2 minus 2 over x minus 1, and the plus 2 is standalone. That's why you will have three asymptotes. Two of them are vertical, x equals to 1 and x equals to minus 2, and the horizontal asymptote is y equals to 2. Next part, we need to sketch the graph of f on the set of axes below, label the asymptotes with the equations, and label the maximum turning point and the point of inflection with their coordinates correct to 2 decimal places. And we need to label the intercept with the coordinate axis. That means we need to include both y-intercept and the possible x-intercepts. Bear in mind we need to adjust the CAS viewing window from minus 10 to 10 and from probably minus 6 to 16. So we can closely match the set of axes on the exam booklet. And then we can identify the following points. This is the y-intercept and this is the x-intercept. This point is actually a local maximum, and this point 6.7882, 2.451. It's a point of inflection. And on the other side, we also have x equals to minus 5, y equals to 0. And by the way, in terms of the rounding, I included the maximum turning point, the x value, with more decimal places. So you have to be rounding these 1 to 2 decimal places. And if you do not have enough float, say, the CAS only displays 4.445, then you probably would have rounded that incorrectly to, let's say, 4.45, which is not true. So you have to round it to 4.44 according to the more decimal place version. And then you can actually get, let's say, the graph sketched. So something along these lines. Make sure you clearly include the three asymptotes with the equations labeled, and the middle branch is not symmetrical, and this is 0, 7.5, the y-intercept labeled. And this branch, make sure you demonstrate the correct asymptotic behavior, and probably you should notice this right branch is slightly closer to the vertical asymptote compared to the left branch with respect to the left vertical asymptote, okay? And label there are 6 points. Part D was a challenging question involving the parameter k. So we would like to find the values of k for the graph g of k to have 2 asymptotes. Well, if you use the expand button again, you will be able to get, for example, some general form. But in this case, I defined it with respect to x and k. So let's say if we have a repeated factor, then the bottom will just be, let's say, x plus 2 squared. In fact, when you expand this case, you will just get 2 asymptotes, one vertical, one horizontal. And also there are other 2 cases where you can get some cancelable factors. And here are the steps for necessary analysis. Therefore, we totally have 3 values. The first one is k equals to minus 2. Remember, it's for a repeated factor under the vinculum. And for the cancelable factor, we might get, for example, x minus 3 over 2 here. So you can cancel out the 2x minus 3 from the numerator. And this one reduces to a rectangular hyperbola. And it does have 2 asymptotes. And the other case is when you get an x plus 5 and an x plus 5. So you can get another rectangular hyperbola, which gives you k equals to minus 5. The second part says given that the graph of GK has more than 2 asymptotes. That means we cannot take these values. Then we would like to find for what values of K will the graph of GK have no stationary point. So basically, you can derive the function gkx with respect to x and solve it equal to 0. Here I use the zeros command rather than solve derivative equal to 0, x. And we can clearly get the two expressions. And we just need to make sure these two expressions disappearing. So for example, this is in the structure of solutions to quadratic equation, I suppose. And we just need to make sure under the square root, this quadratic expression is less than 0. And we will get k less than -5 or k greater than 3/2. Necessary working should involving, let's say, solving derivative equal to 0, but you can't just quote, in my opinion, the derivative equal to 0 the equation. You have to actually show your solutions to this equation and then grab this part less than 0, solve again, you get the desired two sets of values. Here is a further discussion page to the previous part. Actually, this one should be D. I'll fix that later. We may possibly argue that, let's say, if you look at the structure of the solution here, you can equate the denominator to 0 and argue, oh, the two x expressions will disappear. But the thing is, if you substitute k equals to -3/2 into the family of function and solve derivative equal to 0, you could actually get x equals to -7/4 and sub that back, you will get a 338, which is not very easy to observe if you just plot the graph. So here, I changed the scales from -500 to 500 along the y-axis, and I will see there is a middle branch, which indicates a local minimum. That's why in our answer to the previous part, we must not include k equals to -3/2. Second question is complex number, only 9 marks, but this is a decent complex number question. For example, we look at the polynomial first, which is z to the power 3 plus alpha z squared plus beta z plus gamma. And z is a complex variable, alpha, beta, gamma are real values. It can be written as a factorized form. z1 is a real number, and z2 and z3 are complex numbers. So we need to assume we apply conjugate root theorem. Therefore, if we want the relationship between the two complex solutions, we might say, okay, z2 is z3 bar, or z3 is z2 bar. Of course, there was an underspecified condition saying these two solutions should be having non-zero imaginary parts, because real number set is still a subset of complex number, and this issue arises in the second part. The next part, we need to determine the values of alpha, beta, and gamma using the three given conditions. So let's assume z2 and z3 are complex numbers with non-zero imaginary parts. Then we can define z2 as a plus bi and z3 as a minus bi. The next thing is we will define p of z as z minus z1, z minus z2, and z minus z3. And we can solve three simultaneous equations using the three given conditions. For this real solution z1, the constant a and the constant b in the solution. Then we will be able to get, let's say, a is 0, b is -3, z1 is 3. Or a is 0, b is 3, and let's say z1 is still 3. So we can go back and define z1, z2, and z3, and put it back into the polynomial. And just notice these two complex solutions are purely imaginary, plus or minus 3i. So you might want to use a bit by hand calculation, but this is not needed if you have your CAS calculator fully utilized. Once you put them in, you can use the expand button to get z cubed minus 3z squared plus 9z minus 27. Therefore, you can directly state alpha, beta, and gamma, which will be -3, 9, and -27. Of course, there is a special case. If we do consider Z1 and Z1, Z2, and Z3, like these two, Z2 and 3, they are purely real. You might find Z2 and Z3 can be 3 and -3. So solving that equation, you'll be able to get a Z1, which is -3/5, and then expand the corresponding polynomial. You will be able to get, let's say, +3/5, -9, and -27/5. And this was also indicated in the examiner's report for 2021 Specialist Mathematics Exam 2. And this case was marked accordingly. But that was not required, I think, for the 3 marks. So if you are able to get, let's say, this chunk of work, then you were not expected to get the 3 solutions here. Now, the second part of the question starts with considering the point z4, which is √3 plus I. This is a familiar complex number. If you write that in a polar form, that would be 2c pi/6. We want to sketch the ray given by argument z minus z4 equals to 5 pi/6. Just be very careful. Whenever you are sketching this ray in terms of argument equals to an angle, you have to exclude the originating point. In this case, label the z4 at the correct location, which is √3 plus I. And then the angle of inclination is 5 pi/6. So with an open circle here, you might get, let's say, a dashed line here. Well, this is not included in the ray, so this is just a reference direction, horizontal direction with angle 0. And then you measure roughly 150 degrees. And then extend the ray from the originating point here. Okay? And a quick check is you should be able to form, let's say, an equilateral triangle with side lengths 2. And therefore, ideally, the ray should cut through exactly at 0, 2. This y-intercept here. Okay? All right. We say the ray intersect the circle, z minus 3i equals to 1, and it divides the circle into a major and a minor segment. So on top of the previous ray, we need to sketch the circle on the Argand diagram, and then find the area of the minor segment. So first of all, let me replicate the previous work here. Yep, this was the ray we sketched. And then notice this circle has a center of 0, 3, and a radius 1. So one vertex should be here, and another vertex should be here at 0, 4. And we just draw a nice circle, and it's highly recommended for to get a pair of compasses if you could. And yep, and then you need to find the area of the minor segment, which, if you can see my cursor, it's finding this little region here. And there are different approaches to this one. So one possible approach I hope you could see is using a translation to identify the angle subtended by the arc at the center of the circle. So let's say if we translate this circle back to here around the origin, and we can also translate, let's say, the ray by 3 units down. And then you'll be able to see, okay, this is exactly the same triangle as this one. And this is exactly the same segment as the part required. Okay, so what I'm saying is translate both the circle and the ray by 3 units down. So the center is at the origin, and then you can identify the angle, which is 60 degrees, involving an equilateral triangle. And then you can just apply the segment formula, half radius square times angle minus sine of the angle. Radius is 1, angle is pi/3. Chuck them in, you'll be able to get this answer, either pi/6 minus √3/4, or let's say in the combined form, 2 pi minus 3√3 divided by 12. Question 3 is concerning a thin-walled vessel, and it was produced by rotating the graph of a cubic function around the y-axis for y between 0 and a capital H. All lengths are measured in centimeters. So this is the diagram. First part, we want to write down a definite integral in terms of y and a capital H for the volume of the vessel in cubic centimeters. So just be mindful, this is not x squared, this is x to the power 3. So you have to, let's say, isolate x first. In this case, rearranging gives you x to the power 3 equals to y plus 8. Take a cube root both sides, you get x, but for the volume of revolution in the formula, you have to get x squared, which means you are going to use v equals to pi 0 to capital H x squared dy. So you sub in the x squared here, and then you may use your CAS calculator to integrate this expression. By the way, CAS, especially TI, cannot distinguish between lowercase and uppercase letters. So if you use the small h here, when you transcribe the answer on the exam booklet, you will have to write capital H rather than small h. So this is the final answer. There are other equivalent forms for this one. For example, student might have expanded this expression, but I don't think it's necessary. As long as it's correct, just keep one version of the correct answer on the exam booklet. And then water is poured into the vessel. However, due to a crack in the base, water leaks out at a rate proportional to the square root of the depth h of water in the vessel. So now it's changing the capital H to a small h, because small h can be anywhere between 0 and a capital H. This is like a variable. And it tells you that dv dt, the rate of the volume with respect to time, is minus 4 root h. V is the volume of water remaining in the vessel after t minutes. This part needs to use a related rates or chain rule to get the h dt. So what I'm going to do is first, I will replace the capital H with small h, and then differentiate this expression, either by hand or by CAS. So you'll be able to get a pi h plus 8 to the power 2/3. Then we will need to apply the correct chain rule. One possible version is dh dt equals to dh dv times dv dt. So dh dv is the reciprocal of this derivative, and dv dt is minus 4 root h. And you must show clear substitution, especially when you multiply this negative quantity. Make sure you put a bracket around it, otherwise it may look like a fraction subtract 4 root h. Then it's the answer provided in the question stem. So 2 marks, maybe you need to show the correct derivative, and then 1 or 2 steps, writing down the related rates chain rule and subbing the derivative expressions correctly. The next thing is find the maximum rate in centimeters per minute at which the depth of water in the vessel decreases. So it's asking for the maximum rate of decrease. Well, it's a bit tongue twisting, but what I want to say is you can't decrease something by a negative rate. That means you are finding the lowest rate, lowest negative rate, and then take the magnitude. So this was the purpose of the question. And you need to find the corresponding depth in centimeters. So these are the keywords when we put them together during the reading time. Maybe we need to draw, let's say, a full picture. Okay, what I'm doing here is, yes, I did use the previous result without a negative. So I'm treating this one as a positive quantity, then trying to find the maximum positive value. F max, or draw a graph, that's fine. You will get a h equals to 24. Then you would substitute this one into the rate of change expression. This is the exact answer, but you have to round that to 2 decimal places. So how we present the answer as our response. If I were writing the response on the exam booklet, I would say absolute value dh dt maximum equals to 0.62 centimeters per minute when the depth h equals to 24 centimeters. Part 3. Let capital H equals to 50 for a particular vessel. That means the vessel can only hold up to 50 centimeters high of water. Okay. The vessel is initially full and the water continues to leak out at a rate of 4 root h centimeters cubed per minute. That means we can still apply the previous rate of change expression. Okay. But the thing is, let me just fast forward a little bit. We would like to add water simultaneously. So we need to consider a total rate of change of volume. It's the inflow rate minus outflow rate. And we try to make sure the vessel is not overflowing. Without something doing something means without an object doing something means the vessel does not overflow. Make sense? Here, the total rate of change dV dt is the inflow rate minus the outflow rate. So the maximum outflow rate occurs when you take capital H equals to 50, which can be slotted in here. And for the vessel not to overflow, we would need the total rate of change is either equal to 0 or less than 0, which means overall the volume of the water is either not changing or decreasing. Then you would get a dV dt in, which is like a constant rate of inflow is less than or equal to 4 root 50. Therefore, the largest possible inflow rate you can apply is 4 root 50, or if you simplify that, that will be 20 root 2 in centimeters cubed per minute. The vessel is initially full where h equals to 50 and the water leaks out at a rate of 4 root h centimeter cube per minute. When the depth of the water drops to 25 centimeter, extra water is poured into at a rate of 40 root 2 centimeters per minute. You can see following the previous part, this one is twice as much the inflow rate. That means you are going to refill this vessel back to 50 from 25. Okay, so this is looking at the refilling stage. And because the inflow rate has changed, you need to apply the related rates again and find a new differential equation for dh dt. In this case, your new dv dt is 40 root 2 minus 4 root h. And the dh dv is still this guy. Therefore, your dh dt is that divided by pi h plus 8, 2 on 3. Just follow the chain rule you did in the previous show that part. And then this is a new differential equation involving h. You are going to find the time difference or the time change. That's why you have to make sure you reciprocate or flip over this differential equation so you can integrate with respect to h. Once you flip that, make sure you read the question. It's not starting from initially full. We are treating the refilling stage from 25 to 50. Refill means from 25 to 50. So you are going to integrate your new dt dh from 25 to 50. And this can be done by CAS calculator once you set out this definite integral. The answer is 31.4 minutes. So that's the first three questions. Then I'm going to quickly talk through question 4. Question 4 had a large block of 3 paragraphs. So it describes a car performing a stunt move along the track. You need to look at the diagram. So it's moving from A to B, and it has gained a bit of speed. Then it travels up, and this is where it will follow a projectile path. And hopefully the car, once it completes the stunt move, it will land on this ramp with 10 degrees to the ground, downwards. And this point of landing potentially has a coordinate pair 16, 4. Okay, so that is the brief visual scenario you need to look at. At point O is where the car left the ramp. The speed is u meters per second and it takes off at an angle theta to the horizontal direction. After it passes point O, it follows the trajectory where the position of the car's rear wheels relative to point O at time t seconds after passing O is given by this vector function here. Well, this is definitely projectile motion subject to gravitational acceleration only. Okay, so what you do first is show that the path of the rear wheels of the car while in the air is given by this Cartesian equation. So what you do is extract your x and y component from the vector function, which is u cosine theta times t, and y is u sine theta times t minus half gt squared. So to show this given result, you have to eliminate the letter t, which means rearranging x, you will get a t equals to x over u cosine theta, and show a clear substitution into the second equation. You will find for the first term, u cancels u, and the sine divided by cos is tangent. And then don't forget when you sub into the second part, t squared, put a bracket, square everything. So eventually you can derive this is the equation of the pathway in terms of x and y only. And the next part relies on this result here. We've been told the theta is 30 degrees for the projection angle. The minimum speed is the u here we want to find. We must make sure this pathway contains, let's say, point C, the second section of the track or beyond point C. We can simply substitute, let's say, 16 and a 4 into this equation, and also theta equals to pi over 6 or 30 degrees. Then we can solve for u greater than 0 because we are looking for a speed. The answer is 17.87 meters per second. And here is a possible way you could execute your CAS calculator. You might also define this function as f of x and then slot in the two values and the theta value, and then just use the solve button to get the positive u value. Part C, I think class pad users will be having a bit of trouble here. What I would say is, if the rear wheel of the car joins up smoothly with the beginning of the second section of the track at point C, that means first you need to sub in x and y, 16 and 4, into the equation. Then, looking at the diagram, here's the diagram. Even though this is a 10 degrees angle, it's actually a negative slope. That's why to make sure it's smoothly joined, you have to use a negative gradient at x equals to 16. The negative gradient is negative tangent 10 degrees or tangent 170 degrees. Okay. So the other equation you might get is tangent minus pi over 18 equals to derivative of this equation when x equals to 16. So I actually equated the derivative to the correct tangent value and also subbing x equals to 16. Doing these two steps will give us two simultaneous equations involving theta and u. And by convention, u is a speed greater than 0, and the angle of projection when the car left the point O should be an acute angle. That's why you need the two constraints to solve for, let's say, the u value and the theta. And eventually, once you get the u and the theta, you need to convert the theta value to degrees. That's why at the end I multiply by 180 divided by pi, which is 34.1 degrees. Okay. You might, let's say, use your CAS calculator in a different way, but I think this can outline most of the steps you will need to effectively solve this problem. The last two parts. The car accelerates from rest along the horizontal section of track AB, where its acceleration is given by A equals to 60 over V. And V is the speed at S meters. Usually we use X, but in this case we used S. And we want to show that V equals to 180 S to the power 1/3. So basically this is applying, let's say, A equals to V dV ds. Usually we use V dV dx. Equate that to 60 over V and you get a dV ds equals to 60 over V squared. Then you can separate the variables or flip it over and integrate both sides. Here I demonstrate a different approach, like change a variable here, applying the boundary conditions, and then you will be able to get S equals to, let's say, W to the power 3 divided by 180, evaluated between 0 to V. So doing this avoided an explicit step to find the integration constant C, but you might just get a plus C as usual and a sub in to find the C, okay, and complete the rest of the steps. So make sure you either acknowledge the plus C and find it by substitution, or apply suitable definite integrals, especially for the dummy variables. Well, part E, after the car leaves point A, it accelerates to reach a speed of 20 meters per second at point B. However, if the stunt is called off, the car immediately brakes and reduces its speed at a rate of 9 meters per squared second. So this is a deceleration. A equals to -9. It is only safe to call off the stunt if the car can come to rest at or before point B. Otherwise, it will be, still traveling along the ramp. Point W is the furthest point along the section AB at which the stunt can be called off. We would like to find how far is point W from point B. Give the answer in meters correct to 1 decimal place. I think it's a good idea to redraw a quick diagram, just highlighting the section A to B, and the point is W in the middle. First, we would like to design, let's say, a horizontal track such that I can gain a speed of 20 meters per second. That's why I would substitute V equals to 20 into the previous result and get, let's say, the minimum distance required. That would be 400 over 9 meters. The next thing is we can divide the section into two parts. From A to W, it is the acceleration stage, following A equals to, let's say, 60 over V, and it also follows that V equals to 180 S to the power 1/3, okay? So that's why this section we still apply the previous model. But if W is the largest point, the longest point, I can start to step on the brake and decelerate the car. Then for this section W to B, you will have to use, let's say, acceleration -9. So what I want to find is the distance from W to B, so I set it to D meters. And then A to W is 400 over 9 minus D. Therefore, we can write AW in terms of D as well. So from A to W, because V equals to 180 S to the power 1/3. This is the distance, and we can sub that into the velocity function. So I can express the velocity at a W as 180 times 400 over 9 minus D to the power 1/3. Then from W to B, A equals to -9, and the stopping distance is X equals to D. So for WB, I will apply, let's say, constant acceleration formula. For example, V squared equals to U squared plus 2AS, because our final target is to stop the car fully at a point B. And then we can just apply, this formula. Notice that this is one equation in terms of D, and therefore we can sub everything in and solve for D directly using the CAS calculator, which is 16.4 meters. Of course, if you try other methods like integrations, that will also do, but you have to acknowledge two parts, two distances, and add them up equal to 400/9, which is essentially the same way before, but it takes more working and more steps to derive the suitable definite integrals. So I just quickly show you the snippet I did here. And don't forget, if you found, let's say, the accelerating distance, you need to take that away from the total distance 400/9, which is 16.4 to 1 decimal place. Question 5 is now out of the study design because even though we had some constant acceleration paths in the question, it's all based on the idea of mechanics. That's why I will skip this question, okay? So I'll quickly show you a couple of pages here. Having said that, this was still a good question, a decent question, which I think separated a lot of good students.